My name is Rick Spedden, and I'm on the north side of Little Cottonwood Canyon in Utah. This is a follow-up video to a presentation I made at the 2020 Geological Society of America annual meeting. In that work, I presented evidence that when Lake Bonneville was at its high stand, a massive earthquake on the Wasatch Fault resulted in surging and tsunami in the lake, and that the Bonneville Flood immediately followed this event. From the fact that over 5 square miles of submerged glacial till land masses under Cottonwood Heights in Sandy, Utah were dragged several hundred feet out to sea, and that the impact carried up into the Cache Valley, this had to be an extraordinary event. I was hopeful that once I got this information out there, some of those who study Lake Bonneville might re-examine their data relative to the lake level leading up to the flood and contribute to a discussion relative to the magnitude of the surging. That didn't happen. A couple of weeks ago, I was on a bike ride like this one going up into Little Cottonwood Canyon when I realized I was going right by evidence of surging and tsunami in Lake Bonneville at the time of event T. The really exciting thing about this evidence was that it gives an indication of magnitude, and it even comes with a timestamp. It was one of those, oh, wow, moments in science that is just so much fun. Before I get to that, though, what I'd like to do is just give you a brief history of Lake Bonneville right up to event T. It sort of sets the stage for it. Lake Bonneville started its rise about 30,000 years ago, when lava flows in southern Idaho diverted the Bear River into the Great Basin from its previous course into the Snake River, the Columbia River, and ultimately the Pacific Ocean. Lake Bonneville probably achieved its high stand and developed a stable outflow at Red Rock Pass sometime between 18 and 22,000 years ago, but that is a point of debate. As Lake Bonneville rose, the Earth was in an ice age. The Laurentide ice sheet was sweeping down over New England. In the west, the northern ice sheet was pushing down towards its maximum in Montana. Glaciers were forming in the upper reaches of the Wasatch. The Laurentide ice sheet achieved a glacial maximum around 22,000 years ago. At that point, the global climate started an abrupt warming period, initially due to a long cycle increase in solar radiation. The glaciers in the Wasatch achieved a maximum at about the same time as the Laurentide ice sheet. A team, including Dr. Benjamin Labs of North Dakota State, did some fascinating work on dating the moraines in the Wasatch. They determined that the Bell Canyon terminal moraine reached a maximum about 23,000 years ago, but the spread in the data resulted in an error margin of plus or minus 1,200 years. In Little Cottonwood Canyon, the well-defined 300-foot high lateral moraine across from me here achieved a maximum around 20.8 thousand years ago, but the date on that has an even larger error margin of 2.2 thousand years due to the variability in the boulders tested. When the Little Cottonwood Canyon Glacier achieved its maximum, the glacier filled the canyon from where I am here over to the top of the southern moraine. Lake Bonneville in back of me was nearing its high stand, and the glacier may have been calving icebergs into the lake. The Laurentide ice sheet and the glaciers in the Wasatch started to retreat at about the same time. This brings us to my part of the story. In the previous video, I presented evidence that the event T earthquake coincided with the Bonneville Flood. In that first presentation, I did not put a date on the event T earthquake other than to present physical evidence that it coincided with the Bonneville Flood. Specifically, that the landforms altered by the event T earthquake and the subsequent surging in Lake Bonneville showed signs of a rapidly falling shoreline and no evidence of a stable shoreline. In this video, I'm going to present evidence that all of that occurred 17.4 thousand years ago with an air margin of plus or minus 300 years. Now, geological dating is an evolving science, and when dates are referenced, you need to know on what they were based. A lot of the recent work is based on how much of an isotope, such as beryllium-10 from the atmosphere, has been deposited on an object since it was first exposed. This has to take into account local environmental conditions, and the air margins can get quite large if different samples from various rocks in a location vary greatly. Plus or minus 300 years at 17 thousand years ago suggests a pretty high confidence if the underlying assumptions hold up. The folks up at Utah State are some of the most knowledgeable out there regarding the failure of the Lake Bonneville outflow at the north end of the Cache Valley. They have published Lake Bonneville timelines which place the date of the Bonneville Flood at the same 17.4 thousand years ago that I am using, but theirs are based on a completely separate set of data which combines their own work and that of others up in the Cache Valley. Researchers in Idaho have done beryllium-10 analysis on deposits from the Bonneville Flood debris fields up near the Snake River in that state, and that work puts the date of the flood at 17.5 thousand years ago, plus or minus 900 years. That's 3 different sets of data pointing to a very narrow date range. So, until better data comes along, I'm going to say the Bonneville Flood occurred 17.4 thousand years ago and on a Tuesday. If you get into discussion on dates, just make certain you know what the basis is. In recounting the story of the event T day, I'm going to tell it as if I was using the Wayback Machine in my basement, but in reality, I'm just reading the landscape and I'll check it against data generated by others, not necessarily taking into account their interpretations. By the time of event T, the glaciers had been receding in fits and starts for 4,000 years or so. Retreats and advances create a series of terminal moraines as a glacier recedes. G.K. Gilbert identified some of those moraine segments in his work. At the mouth of Little Cottonwood Canyon on that day, the waters of Lake Bonneville formed a small cove between the western extremes of the northern and southern moraines. Glacial boulders were scattered at the foot of the glacier and in the shallow waters of the canyon's delta. The glacier had done a steady job of delivering the boulders and silt to wherever it intersected with the lake, but then the lake waves would have scattered the silt to form the massive delta going out into the lake, and the boulders would tend to collect right there at the intersection, and they were probably concentrated in bands marking the various terminal moraines during the retreat. At this point in time, the glacier was far below the high stand where it had filled the mouth of the canyon, and really what we are looking at is a resurgent tongue of glacier which had advanced in the very center of the valley and probably extended within a quarter of a mile of the shoreline at least, and possibly all the way to the moraine at the lake shore. The foot of the glacier would still be somewhat of a vertical wall of ice with blocks breaking off, and it would also have the typical cave at its base where there was a river of glacial meltwater running out from underneath it. It was at this point in time that the event T earthquake hit. In that event, the Salt Lake Valley along the Wasatch Fault may have dropped 4 to 10 feet. And if I read the USGS literature correctly, these types of displacements occur in a time frame measured in seconds. Now, I'll have to admit, that rapid displacement seems incredible to me. Of course, the shaking would have lasted longer as the slip propagated along the fault. The shaking would have produced a seiche in the constrained basin of the Salt Lake Valley. Now, this is a standing wave in a basin of water set up by vibration. It is said to have occurred in the 1959 Hegman Lake earthquake in Montana, and on a smaller scale it regularly shows up in swimming pools in California. Event T probably also initiated a tsunami. This is a long wavelength but very fast-moving shock wave, which is produced by the energy generated by quickly dropping a column of water. Water hammer in a pipe is an analogous phenomenon. The deeper the water, the more energy in the resulting wave. The tsunami could easily have transmitted up into the Cache Valley, only to be concentrated as it approached Red Rock Pass, as the valley tends to get narrower and shallower. Tsunami in common parlance has also come to be used more broadly to include a displacement wave, where a landslide into a lake produces a large wave, or someone does a cannonball into that pool in California. I will stick with the original definition of a fast-moving shock wave. I think the other deserves a more specific name, such as displacement wave. In the previous video, I introduced a third concept, surging. I based this on simple physics. When one side of a large body of water is dropped, the level in the basin has to equalize. The whole body of water will start to surge towards the lower side. In the Salt Lake Valley, that deep water surge would come from the northwest and the main body of Lake Bonneville. As the surge moved up the slope of the east side of the valley, all that energy would get concentrated into a massive wave hitting the lower slopes of the Wasatch Mountains. The momentum of the surge would create a sloshing in the Bonneville Basin, generating a corresponding drop in level in the western reaches before sloshing back. While either surging or tsunami could have caused the failure at Red Rock Pass, I think it was surging which caused all the shifting of land masses near the mouth of Little Cottonwood Canyon. When the wave of the surge coming from the open reaches of Lake Bonneville from the northwest hit the Wasatch Front at the mouth of Little Cottonwood Canyon, its force would have slammed into the glacier. The cave in the face where the glacial melt river flowed would allow the surge to force in under the glacier. The crevasse-ridden ice of the end of the glacier would have lifted up to form a field of icebergs. Lifting the front end of the glacier out of the way, the force of the surge would have driven on towards the corner where the glacier and the southern moraine meet. The force of the surge would have hit the slopes of the moraine like the jet of water in a placer mining operation, blasting out the silt, sand, and clay, and leaving a rounded and deep indentation in the lower slopes of the moraine. Advancing up the canyon, at one point the glacier would just present too thick and solid a block of ice to be lifted up and out of the way. At this point there would be an abrupt line on the face of the moraine where the glacier refused to yield on that Tuesday. And there is. It is like someone took a photo of the event. More importantly, The blasted out area would also give us an indication of how high the surge was. It does that also. Finally, the event would have given us one more piece of evidence supporting that this is the only plausible explanation. The advancing surge would have swept up into the maelstrom the rocks and boulders from a sequence of terminal moraines in the shallows under the lake at the mouth of the canyon. Videos of floods transporting rocks and boulders are plentiful on the internet. When the boulder debris-laden front of the surge hit the southern lateral moraine corner and forward momentum stopped, the surge flow was directed up the slope against gravity. All the rocks and boulders immediately settled out. A natural gravity separation of the rocks occurred, with the smaller rocks getting carried higher on the slope and the larger boulders dropping out immediately. Boulder deposits like this are a known effect in coastal tsunamis, and there are numerous papers on the subject. This boulder field is not a scree slope. There is no source outcrop above the field, and the smaller gravel is missing. It is not an erosion feature from water above running down. The shape of the gullies are all wrong, and the mass balance doesn't work. Too many large rocks for the volume of glacial till removed. Finally, it is not a rock fall from higher in the canyon carried down by glacier. The distribution along the face of the moraine is wrong, and the glacial till is missing. This is the upslope debris field of a massive wave. The eastern portion of these boulder fields has been quarried for ornamental rocks for homes in the area. The scooped out shape of the wave's impact is actually apparent in this section. The contractor just picked up the boulders. He didn't have to dig for them. Fortunately, the western section is still intact. The boulders almost fill the scooped out areas in this section. The gravity separation is very apparent and eerily consistent. The abrupt end of the boulder field on the east side as you go up the canyon indicates where the solid part of the glacier extended to on that Tuesday. The height of the boulder field above Lake Bonneville gives us an idea of the height of the surge. Near the glacier cutoff, it runs about 140 feet above the Lake Bonneville high stand. There are spikes which actually run as high as 170 feet. I think the most likely scenario is that the first 300 to 500 feet of the glacier was hollowed out underneath enough by the glacial melt river that it was lifted by the surge. The floating ice, remember icebergs are 90% underwater, put a cap on how high the boulder debris field goes adjacent to the glacier. Where there were breaks between the sections of glacier as it was lifted, the debris field spiked higher on the slope. When studying the energy of the surge and impact on other areas of the lake, we should be thinking in the 140 feet to 170 feet above Lake Bonneville high stand range, realizing that landscape topology can focus or disperse wave energy. To put things into perspective, the 2011 Japanese tsunami was estimated at 30 feet high and the 2004 Indonesian tsunami at 100 feet. Videos of those events give an idea of the impact these waves can have. If the rocks in this boulder field were dated, I think they would be found to coincide with the Bonneville Flood and with the debris field I previously identified as the Bell Canyon Flood. I think the scale of surging I was suggesting in the Part 1 video has been difficult for people to imagine. When you are standing on Little Cottonwood Canyon Road looking up at the boulder field, remember that you are standing about 40 feet above the elevation of Lake Bonneville on that day at that point. don't underestimate the magnitude of this event. This is the north side of Little Cottonwood Canyon, just east of the Wasatch Fault. In fact, the fault scarp falls off right in back of me here. This location is about 60 feet above the high stand level of Lake Bonneville, and I'm seated right in the middle of the north lateral moraine field. On this side of the canyon spreads out, and the glacier would have done the same, so it's a rather indistinct moraine aside from all the boulders sitting about. Dr. Labs and his associates did dating work on the glacial boulders in this area. The dating of these boulders was revisited by Dr. Benjamin Quick, then of the University of Utah, in a 2020 collaboration. One of the boulders they tested is the one right behind me. In fact, you can see on top the area where they chipped out a section to take back to the lab and do the analysis. They dated the boulders in this area at 17.4 thousand years ago, plus or minus 300 years. Now that's a very narrow error margin on that type of dating, and it suggests a good deal of confidence in that date. That puts these glacial moraine boulders as being placed roughly 3,000 years after the glacial maximum, which formed the substantial southern lateral moraine across the canyon from me here. They attribute this date to a second, smaller glacial advance they call Pinedale II. However, these boulders are placed too far down the canyon to reasonably have been placed at that point in time by a resurgence. That would have required a resurging tongue to come down and around the corner on the sunny side of the canyon to achieve this point without leaving any other evidence that there was a resurgence on this side or the other side of the canyon. Now, this is where it gets kind of exciting, because I believe what they really captured was the date of the Bonneville Flood. What would have happened when the surging occurred is that as the wave rolled up against this side of the canyon, it would have dragged some of the boulders up on the slope down again. In the process of dragging those boulders down the slope, it would have also sandblasted the surface with all the debris and sand that the wave would have been carrying. That would have established a new surface. This would explain the very small deviation in dating of the samples and the very close agreement of the 17.4 thousand year ago date to the dates others have come up with looking at the Bonneville Flood evidence in Cache Valley and in Idaho. Dr. Labs and his collaborators have done some really fascinating work on the glaciation in the Wasatch. I thoroughly enjoyed reading the papers. I like the fact that their expertise and hard work has set the stage for a broader understanding of events beyond just the glacial advances. For a field of rocks, this one here at the mouth of Little Cottonwood Canyon is a pretty interesting one. It might just warrant a geological marker for the significance of the story it tells, and at some point, I hope Salt Lake County will also correct the panel at the G.K. Gilbert Geologic Park, which speaks to a graben at that location. The real story is a lot more interesting than that. I thought that once I finished the stories in this part 2 video, I'd be done and I could go focus on endeavors in other areas. Unfortunately, just like with the Graben, the Kama Fissure, the Dry Creek Island, the Bell Canyon Flood, the Little Cottonwood Boulder Field, and the Labs boulders, there was just one more thing that, in the back of my mind, seemed a bit off. I started to pull on that thread, and a whole different fabric of underlying assumptions related to Lake Bonneville came unraveled. So, at the same time I post this Part 2 video, I am also posting a Part 3 video. Part 3 is not for the faint of heart, but if you have interest in these areas, it changes things. If I am correct, you have a front row seat as science evolves. For those not formally trained in geology, read, look at the data, travel to the sites if you can, develop your own opinions. Science needs everyone. Understanding how things work should just be a part of your life. If your time is limited, start with physics and economics.